Imagine pouring a glass of water from your kitchen tap. It looks clean. It tastes fine. But what if I told you that inside a device smaller than your forearm, water is forced through a maze so complex that it can trap particles thousands of times smaller than the width of human hair? Most people never think about this. Yet every day, billions of gallons of water pass through filters engineered with astonishing precision. Think about this. A modern water filter begins its life deep underground, inside mines, forests, chemical plants, and factories scattered across multiple continents. Materials travel thousands of miles before they ever touch a production line. And this is where it gets truly extraordinary. Some of the substances inside a filter have surface areas so vast that a single pound can contain enough microscopic pores to cover several football fields. Today, we're stepping inside one of the most fascinating manufacturing systems on Earth. You'll see raw minerals transformed into advanced purification technology. You'll hear the roar of giant mixers, watch robotic inspection systems scan for invisible flaws, and discover why one tiny defect can send an entire filter straight to the scrap bin. What happens next surprised even experienced engineers. Everything starts with activated carbon, the heart of many household water filters. Manufacturers often produce it from coconut shells harvested in countries like Indonesia, the Philippines, India, and Sri Lanka. Farmers collect mature shells, dry them under tropical sunlight, and ship them to carbon processing facilities. What looks like agricultural waste will soon become one of the most powerful filtration materials ever created. Inside specialized plants, those shells enter giant furnaces operating at temperatures between 600 and 900 degrees Celsius, or roughly 1,100 to 1,650 degrees Fahrenheit. Oxygen stays extremely limited. Instead of burning, the shells carbonize. The process leaves behind an intricate structure packed with microscopic pores that can capture chemicals, odors, and contaminants from water. But here's what nobody tells you. Carbonization is only the beginning. Engineers activate the carbon using steam or specialized gases at temperatures approaching 1,000 degrees Celsius. During activation, millions upon millions of microscopic pores open inside each particle. The result is astonishing. Just 1 gram of activated carbon can contain a surface area of more than 1,000 square meters. The next key ingredient often comes from deep underground. Manufacturers mine silica sand from deposits in the United States, Australia, China, and parts of Europe. Massive excavators remove thousands of tons of material every day. After washing and grading, only highly consistent particles move forward. Even tiny variations can affect filtration performance. For advanced filters, manufacturers also rely on ion exchange resins. These tiny polymer beads begin life in chemical plants where petrochemical feedstocks undergo carefully controlled reactions. Imagine millions of perfectly formed spheres, each engineered to attract unwanted dissolved minerals. They may look harmless, but they perform molecular-level work every second they operate. Then comes the plastic housing. Most manufacturers use food-grade polypropylene or ABS plastic. The raw pellets arrive from petrochemical complexes weighing thousands of pounds per shipment. Before molding begins, every batch undergoes testing for moisture, contamination, and consistency. One failed batch can halt production worth hundreds of thousands of dollars. What happens next creates an environmental challenge many consumers never see. Mining, shipping, refining, and processing these materials require energy at every stage. Manufacturers increasingly invest in renewable electricity, carbon recovery systems, recycled plastics, and sustainable sourcing programs. The race to make cleaner water now includes a race to build cleaner factories. By the time these materials finally arrive at the factory, they have traveled thousands of miles across oceans, highways, and rail networks. But the real mystery is only beginning. Because turning piles of carbon, resin, sand, and plastic into a device trusted with human health requires manufacturing precision measured in fractions of a millimeter. And the next stage is where raw materials become engineering masterpieces. The first stop inside the factory is the molding hall. You hear it before you see it. Hydraulic presses thump like giant mechanical heartbeats as food-grade polypropylene pellets tumble into injection molding machines. The plastic melts at temperatures between 220 degrees Celsius and 260 degrees Celsius, or about 428 degrees Fahrenheit, to 500 degrees Fahrenheit. Molten material rushes into precision steel molds under pressures that can exceed 20,000 psi. Within seconds, the molds cool. Robotic arms swing into position and lift the newly formed filter housings onto conveyors moving nearly 1 meter per second. The smell of warm plastic hangs in the air. Every housing must match dimensions within fractions of a millimeter. A tiny distortion could create leaks months later inside someone's kitchen. Meanwhile, another part of the factory prepares the activated carbon. Massive stainless steel mixers rotate between 40 and 80 revolutions per minute. Carbon particles blend with carefully measured additives that improve flow characteristics and structural stability. Black clouds swirl inside sealed equipment. The sound resembles distant thunder trapped inside steel chambers. What happens next surprised even experienced engineers. The carbon mixture enters compression systems that shape it into solid carbon blocks. Hydraulic presses apply tremendous force, often exceeding hundreds of tons. The material transforms from loose powder into a dense filtration structure capable of forcing water through microscopic pathways. Every pore becomes part of a hidden purification network. Some carbon blocks move into curing ovens. Temperatures typically range from 120 degrees Celsius to 180 degrees Celsius, or 248 degrees Fahrenheit to 356 degrees Fahrenheit. For several hours, heat stabilizes the structure and removes residual moisture. Warm air flows through long tunnel ovens while sensors continuously monitor conditions. Engineers know that even slight temperature variations can affect filtration performance. Now the factory combines multiple filtration technologies into a single cartridge. Activated carbon ion exchange resin beads, fine sediment barriers, and protective mesh layers arrive from different production areas. Automated filling stations measure material by weight with remarkable precision. Some systems maintain accuracy within a single gram across thousands of units every hour. Imagine standing beside the cartridge assembly line. Components click together with rhythmic precision. Conveyor systems move hundreds, sometimes thousands, of units every hour. Workers watch screens showing pressure readings, fill weights, and production speeds in real time. The entire operation feels like a perfectly synchronized mechanical orchestra. Next comes ultrasonic welding. Instead of glue, many manufacturers use high-frequency vibrations around 20,000 cycles per second. The vibration creates localized heat that permanently joins plastic components together. The process lasts only a few seconds. Yet those welds must survive years of water pressure and daily use. Then comes a stage most consumers never imagine. Every filter faces water pressure testing. Pumps force water through cartridges at pressures that can reach 100 psi or more, depending on design requirements. Workers watch for leaks, structural weakness, and abnormal flow patterns. One tiny crack means immediate rejection. Most people never think about this, but a water filter is essentially a carefully controlled resistance system. Water must flow slowly enough to allow purification, yet fast enough to remain practical. Engineers balance pore size, flow rate, and pressure drop with incredible precision. A difference invisible to the eye can completely change performance. Finally, completed cartridges move toward packaging. But before they reach store shelves, another hidden battle begins. Because building the filter is only half the challenge. Proving that every single unit performs exactly as promised is where the factory enters its most demanding phase. And what those quality systems can detect is almost unbelievable. As the filters leave the assembly line, they enter a part of the factory that feels more like a science fiction laboratory than a manufacturing plant. Cameras, lasers, sensors, and artificial intelligence systems watch every movement. Nothing escapes inspection. Most people assume quality control means a quick visual check. But in reality, some factories collect thousands of data points from every single filter they produce. The first inspection often begins with machine vision systems. High-speed cameras capture multiple images in milliseconds while filters move down conveyors at speeds exceeding several thousand units per hour. Advanced software compares every dimension against digital blueprints. A missing component, a tiny crack, or an improperly seated seal can trigger an automatic rejection before a human eye could even notice the problem. Then come the laser measurement systems. Thin beams of light sweep across every surface, checking dimensions with tolerances sometimes tighter than 0.05 millimeters. Think about that. That's roughly the thickness of a human hair. What happens next surprised even experienced engineers. A defect invisible to the naked eye can completely alter filtration performance months later. But dimensional accuracy is only the beginning. Specialized flow testing stations pump carefully controlled streams of water through sample filters. Engineers monitor flow rates, pressure drop, and contaminant removal efficiency. Computers compare the results against strict performance specifications. Every second of testing generates valuable data that helps predict how the filter will behave in the real world. Some facilities push testing even further. Robotic systems repeatedly cycle water through filters thousands of times to simulate months or even years of use. Pumps run day and night. Valves open and close endlessly. The constant hum of machinery fills the room. Engineers deliberately create harsh conditions because failure inside the factory is far cheaper than failure inside a customer's home. Now comes one of the most brutal examinations in the entire factory. Burst pressure testing. Water pressure climbs far beyond normal operating conditions. Some cartridges face pressures exceeding 300 psi before engineers stop the test. Others continue until structural failure occurs. The goal sounds simple. Discover exactly how much punishment the design can survive. Most production facilities reject between 1 and 3% of units during various inspection stages. That may sound small, but in a factory producing millions of filters each year, it represents tens of thousands of discarded products. Automated systems remove those units instantly. They never reach packaging. They never reach consumers. And this is where human skill still beats machines. Veteran inspectors often recognize subtle warning signs that computers haven't been trained to detect. A slight change in sound during assembly, an unusual vibration, a texture that feels different when touched. Decades of experience allow skilled workers to notice patterns hidden inside oceans of production data. International certifications add another layer of scrutiny. Many filters must comply with standards established by organizations such as NSF and ANSI. Independent laboratories verify contaminant reduction claims, structural integrity, and material safety. Manufacturers spend years and millions of dollars proving that their products perform exactly as advertised. Imagine a filter traveling through all of these checkpoints. Laser measurements, pressure tests, leak detection, flow verification, AI inspection, human review. By the time it reaches its box, it has survived a gauntlet more demanding than most people could ever imagine. Yet one final mystery remains. How many of these filters does the world actually produce, and where are they all going? Because beyond this factory lies a global industry worth billions of dollars, an industry that touches nearly every household on Earth. And when you see the scale of that network, the numbers become almost impossible to believe. Now step back and look at the bigger picture. The water filter sitting under a sink or inside a refrigerator belongs to a global industry that produces hundreds of millions of filtration units every year. When industrial, commercial, municipal, and household systems are combined, the total number climbs into the billions. Most people never think about this. Yet every day, an invisible army of filters works around the clock to make water safer for billions of people. The global water filtration market is now worth well over $50 billion annually, and analysts expect continued growth throughout the next decade. Rapid urbanization, aging infrastructure, industrial expansion, and rising concerns about water quality continue driving demand. Think about this. Every new city, factory, hospital, and apartment complex increases the need for advanced filtration technology. Today, China leads global manufacturing volume, producing a massive share of the world's filtration components and finished systems. The United States remains one of the largest markets and technology developers. India continues expanding production capacity at remarkable speed. Germany contributes advanced engineering expertise, while Japan remains a leader in precision filtration technologies. Together, these countries help shape an industry that never stops evolving. The industry directly and indirectly employs millions of workers worldwide. Miners extract raw materials. Farmers harvest coconut shells. Chemical engineers create specialized resins. Factory technicians oversee production lines. Scientists develop new filtration media. Behind every filter stands supply chains stretching across continents and involving countless skilled hands. And this is where the story becomes truly extraordinary. Just 50 years ago, many household filters relied on relatively simple mechanical filtration. Today's systems can target chlorine, heavy metals, organic compounds, bacteria, and even microscopic contaminants measured in fractions of a micron. What once seemed impossible now happens every time someone fills a glass from the tap. Did you know that some advanced filtration membranes contain pores so small that thousands could fit across the width of a single human hair? Water molecules pass through. Many contaminants cannot. The engineering behind that achievement pushes the limits of modern material science. Did you know that some municipal filtration facilities process hundreds of millions of gallons of water every single day? The scale is staggering. Imagine filling entire sports stadiums with clean water, then doing it again tomorrow and the next day and the next. That's the level of demand modern filtration systems support. And here's another fact that sounds almost unbelievable. A single gram of high-quality activated carbon can contain more internal surface area than several tennis courts combined. That's why such a small filter can perform such powerful purification. Hidden inside every cartridge is a microscopic landscape larger than most people could ever imagine. Looking ahead, the next decade may bring smart filters equipped with real-time monitoring sensors, AI-driven maintenance alerts, advanced nanomaterials, and dramatically improved contaminant detection. Future systems could continuously report performance directly to homeowners and utility providers. The filter of tomorrow may be as connected as the smartphone in your pocket. We've traveled from tropical coconut farms and mineral mines to high-temperature furnaces, precision molding machines, robotic inspection systems, and global distribution networks. Along the way, we've seen raw materials transformed into one of the most important technologies in modern life. Most people see only the finished product, but now you know the incredible journey hidden inside every filter. The next time you watch clean water flow from a tap, you'll understand that countless people, machines, and scientific breakthroughs made that moment possible. Engineers designed it. Workers built it. Laboratories tested it. Entire supply chains supported it. And all of that effort exists for one simple purpose: delivering cleaner water to the people who depend on it every day.